Okay, we already have one live link. So I have also created this. Perfect. So we can get started maybe.
Okay. Hello, guys.
Sharing. Yes. Yeah, I think people are already responding on chat. I'll just share the YouTube link as well with them.
Right.
So what I can do is I can already pick some questions that we got from yesterday's response sheet. Okay.
Yeah.
I'll just go one by one. I'll probably give preference to people, those who are there here. Let me just quickly check that. So I'm just picking how to determine whether a problem is a classification problem or a regression problem, asked by Mahika.
All right. So when the variable is continuous and you want to predict some of the values of that variable, it should be a regression problem. If the variable is discrete, or you can classify the variable in several classes, then the problem is going to be classification problem. So I just want to open. Oh,
Yeah, you're already opening it. Okay, okay. I thought I'll share my screen, but yeah, you go ahead. Yeah.
I just want to open Paint, so making myself more clear about that.
Yeah. I think you should also share your screen, maybe, Julian. Yeah.
Yeah. All
Yeah.
right.
Perfect.
What's screen here? Yeah. So when you have a variable, for example, let's say you have this continuous variable, and you have a table, which is your data frame, and your data frame has a lot of features. Let's say these three are the features, and this is going to be the target variable. So if the target variable is continuous, I mean by continuous that has an infinite space, for example, between 1 to 5. So you can have here 0.1324 or 0.2356 or 2.5678. This is a continuous variable since it is an infinite space between 0, which is the low value, and 5, which is the maximum value. And between 0 and 5, there are infinite numbers. So this should be a continuous space. And if that target variable is a continuous space, then you are against a regression problem, because you want to predict a value that is in here in this interval, but the interval has infinite values. So that should be a regression problem. If you have a target variable, I'm gonna make a new sheet in here. If you have the same data frame with 3 features, here I'm gonna say x1, x2, and x3. And I have the target variable here, which is y. But the target variable is not continuous, it's discrete. So we have classes. What are classes? So for example, I have cars. So this car is gonna be Audi. This car is gonna be Chevrolet. And this car is gonna be, I don't know, Porsche. So you can see that here in my target variable, I have 3 classes, which make the target variable to be categorical. So when the target variable is categorical and you can identify the classes clearly, the problem should be classification problem. This is not a regression problem because the variable is not continuous. The variable has clear classes. So it should be a classification problem. That is the difference between a regression and classification problem. Which approach do you follow then? Well, you have to select one technique, one model, and then make the model stage and make predictions and evaluate the model. So it's very straightforward once you have identified what the approach is.
I believe that clarifies things to a certain extent. Yes, Mahika has got it perfect. And now let's go to the next question. I would like to know how and when to use sigmoid function and decision boundary. Yeah. Probably like, Julian, I'm just sharing my screen so that like, we
Yeah.
have shared something today. You can explain it maybe like, if that gives some intuition, I don't know. But yeah, just let me know if it makes sense or not. Yeah, probably like, you can start off. Yeah. So this is a place where like, we try to put sigmoid function. Do you think these slides help you, or would you want to draw it yourself?
Yeah. Yeah. Let's take this slide, for example.
Yeah.
So the sigmoid function is related generally with a logistic regression approach. So if you are focusing on logistic regression, it means that you have identified that the problem is classification, and normally the problem is binary classification. So when to use logistic regression instead, I think is going to be the question. When you have a binary classification problem, which logistic regression approaches very well, or when you have a multi-class classification problem, which I think is better using other models, but you can also use logistic regression. What is the issue with the sigmoid function? Because logistic regression originally is a linear regression. So it seems that like the regression name is because of regression, and it is false. It is because it's a linear regression, but has this sigmoid function that makes the value to be a probability. So you can see here in the red dots that we have the sigmoid function and we have values between 0 and 1, but the values are discrete, they are not continuous. So we have just 0 and 1 as discrete values. So these are two classes, the class 0 and the class 1. Yeah, those red dots, exactly.
Julian, I gave you remote control access to the system, so you can probably access.
All right.
Yeah, you can access, right? Yeah. And also if you want to use Paint, you can. Yeah.
Okay, I think this is a lot of delay, but I will try.
Okay, then I'll let you do it. Maybe I'll stop sharing my screen and you can use it from your end, your system.
Yeah.
Yeah, I'll just stop sharing my screen once again. Yeah, 1 second. Yeah. Yeah, maybe you can just share your screen. Yeah.
Yeah, I'm just gonna use Paint.
Yeah, perfect.
So the sigmoid function is gonna be as follows. And the interesting thing about the sigmoid function is that it transforms a continuous value to a discrete value that then is transformed to probabilities. So as we were seeing in the graph, there are red dots in here in 1, and there are a few dots here in 0. So it means that the variable is not continuous, but it is discrete. So there are 0 values and 1 values. So it means that there is a 0 class and a 1 class. So this line that you are seeing here, that is the sigmoid line, is converting those continuous values from a classical linear regression to a classification problem to be 0 or 1. So that is a probability. And you have obviously the decision boundary that normally is in here, which is 0.5. So it means that whenever you got an output above 0.5, that classification output should be 1. And when you have a classification or a regression output below 0.5, that is going to be converted to the class 0. So this is the relationship between logistic regression and linear regression. Logistic regression is a linear regression, but this sigmoid function converts that output to a probability to be 0 or 1. So it is converted to a classification approach. Whenever the variable is below 0.5, it is converted to 0. And whenever the variable is above 0.5, it is converted to 1. So you have clearly two classes, or it is 0 or it is 1. So this is the use of the sigmoid function. I don't want to state the equation, but I just want to open here Wikipedia. We have the equation here. So you can see here that we are making an approach of a sigmoid function using the logarithm. So this logarithm converts this linear equation into an equation that gives me probabilities between 0 and 1. And then with the decision boundary of 0.5, I convert the values or 0 or 1. So there is a relationship between the original linear equation and the classification approach that logistic regression is doing.
Maybe, Julian, maybe if you can repeat it once again. I think few people are asking for it on Slack. So if you could re-explain once again, if you don't mind, yeah, about the, yeah.
Okay, so I'm just gonna go slower. So imagine you originally have a linear regression approach. So you have just a line between X and Y. And that is your linear regression approach between a variable X, which is gonna be the feature, and the variable Y, which is gonna be the target. So logistic regression is a linear regression with a plus. So we start by seeing the logistic regression as a linear regression approach. Why is it different? Because the equation is not considering a linear equation, but is considering a sigmoid equation. So instead of having a linear relationship, you have a sigmoid function. And this sigmoid function has in here a decision boundary that normally is 0.5. So 50%, if we interpret this as a probability. The interesting approach in here is that we are converting this linear equation from the left to a classification problem in the right. How can we do this? I'm opening Wikipedia, and we have here the equation, so that I'm not gonna state it again. And we can see in the right part that we have a linear regression, just a linear equation between two features. And we have in the left the sigmoid or the logarithm focus. So we are converting our output that should be L into a probability using the logarithm equation. So you can see here that we are stating a P, and this P is going to be a probability. Then we are going to have P here in the left and all the equation in the right. So we are converting our linear classical approach into a probability approach that then using this decision boundary is going to be converted into probabilities and is going to be converted into two classes. So if anything is above 0.5, this is going to be interpreted as a 1. And if the output is below 0.5, then it's going to be interpreted as 0. So we are coming from a linear regression passing through a sigmoid function and a decision boundary to a classification problem. So logistic regression at the end is going to be a classification approach, whether the output is going to be 0 or 1. So we have two classes. And this output is converted using this sigmoid function, and we can interpret the output as a probability. That is because we are using this function and the decision boundary of 0.5. We maybe can change this decision boundary, yes. We can put the decision boundary here, maybe to 0.8. And the interpretation is going to be the same. So everything that is above 0.8 is going to be converted to 1, and everything that is below to 0.8 is going to be converted to 0. So the approach is the same. We have two classes, we have probabilities, but the interpretation is a little different because we have changed the decision boundary. So maybe the accuracy or maybe other metrics are going to be changed and are going to be updated. So it depends really on the nature of your data and what do you want to achieve if you modify this decision boundary. By default, it is 0.5. So everything above is going to be 1 and everything below is going to be 0.
Right. Yeah, I think that's a nice explanation. Yeah, I totally agree. And usually, like, people tend to get a little confused in this particular aspect, I guess. And also, like, if everyone would have gone through, we have given a nice example today as well in the learning module. I think that should also top it up. And I think even this explanation, I mean, like, both of them together, that would be brilliant, I guess. And also Julian, probably like, I'll also run through an example to them, so that like, they can probably like, so that it's also they can see it live. 1 second, I'm just taking the screen share from you. 1 second.
Okay.
Yeah. Please correct me if I go wrong somewhere. And so one thing is like, today what we have done is we tried to give an explanation of what is the difference between linear and logistic regression. So yeah, let me just quickly run through the slides. So basically, in the first place, if we look at linear regression, right? Linear regression is used for continuous values, where it can be predicting the age of an individual or anything like, which is a real number. It can be anything from minus infinity to plus infinity. And when it comes to logistic regression, we primarily use it for classification problems. So classification, again, like, if we have to talk about classification, we have given a bunch of examples here. If in this particular case, we were trying to predict the tumor, based on the tumor size, we were trying to predict whether a particular tumor is benign or malignant. Okay, and we are classifying this way. Similarly, if we look at our previous problem statements that we have worked with, the fraud detection one, it's fraud or not fraud. So it's again a classification problem. And when it comes to multi-classification, it can be more than two categories. So in this particular case, we are trying to classify a waste into 4 different categories. That is, one is plastic, glass, metal, and paper. This is more to do with multi-classification. Usually, like, we end up using logistic regression in classification problems. And in this particular example, we have picked a data set which is basically predicting whether an individual would take an insurance or not based on their age. Okay, this is the data set that we have picked. And what we have done is we have extended the same concept of linear regression that we have used while predicting this particular model. As we can see, this is the age of the, sorry, 1 second. Yeah. So basically in this, on the y-axis, as we can see, we are trying to predict whether a particular individual has taken insurance or not. 1 means they have taken the insurance. 0 means they haven't taken any insurance. Whereas on the x-axis, we can see their age. This is the age that we are talking about. So as we can see, it is very intuitive that people with high age, I mean, people with age above 40, they have taken insurance. That is 1. As you can see, like, this is 1. 1 means people who have taken insurance, and 0 means people who haven't taken insurance. Again, like, it's very intuitive that people who are older would end up taking insurance, which is very intuitive that way, especially in countries like India. They end up taking at a later stage than when they are younger. And now here, what we are trying to do is we are trying to set a cutoff. Here we have plainly applied a linear regression. And what linear regression has done is, like, it has drawn a single linear equation. I mean, like, linear regression line. As you can see, this blue line is nothing but the linear regression. And what we have done here is we have set a cutoff of 0.5. Okay, when we have set a cutoff of 0.5, we are trying to draw a line here. And at the intersection, what we are doing is, like, this is nothing but the decision boundary. This green line is the decision boundary. And the values which are on the left are nothing but like, who have no insurance, and the values towards the right are classified as the individuals who have insurance. Okay, please let me know, like, if it is not clear. I'll try and explain. So this is the decision boundary, and the values on the left are those, like, who don't have insurance, and values who are on the right are classified as those who have insurance. Okay, so and in this case, like, we can see that, like, these are outliers. These two values and these two values are outliers. However, as we can see the model, there are certain values which are not classified well. These entire set of values are not classified well. and also these values are not classified well. This is the decision boundary, as we can see. Okay, technically, like, instead of having this, so for example, if we are still going ahead with linear regression, we end up misclassifying this set of values and also this set of values. Let's imagine, like, we have a very big outlier which is towards the right corner. Okay, then in that case, what happens is our regression line, instead of it being like this, it has ended up being like this. It got distorted due to this additional outlier. So it is not very robust to outliers. And I can't make this statement, but so basically, like, if we can see this, so this particular line has distorted, and due to which there are a lot more misclassifications that are happening here. So this is a very poor fit for that matter. Okay, and here, like, as we said, as we explained earlier, here if we are putting the threshold as 0.5, then we will be drawing a line like this here, and at the intersection we'll be drawing a decision boundary, which is nothing but the green line. And again, as we mentioned earlier, the points that are on the left are considered as nothing but, like, those who don't have insurance, or those are predicted as not having insurance. Those are classified as not having insurance. And the points that are on the right side, they are classified as those individuals who have insurance. Okay, technically, like, here we are misclassifying a lot of variables, a lot of observations. These entire set of observations are misclassified. Again, this is a bad fit. Instead of having this as the decision boundary, it would have been ideal if this yellow line would have been a decision boundary, because that would have been a rather better fit. Okay, now going a step further, right? It would our life would have been much more simpler had we had a model which would predict things like this. Okay, which would connect all these dots, and that's where the sigmoid function helps. What sigmoid function does is, like, it will technically sigmoid function takes in any real value and gives the output in the form of a probability between 0 and 1. As we can see, it gives in the form of 0 to 1. That's where I think Julian has brilliantly explained, like, how it works. And if you are changing your decision boundary, again, like, instead of keeping decision boundary as 0.5, if you keep the decision boundary as 0.8, then you end up drawing a, you end up, I'm sorry. So if you are keeping the decision boundary as 0.8, it would come somewhere here, and we would end up drawing this green line here. Okay, so that is how we define our decision boundary, or whatever it is. So I hope that makes it clear, but if there are any questions, we'd be happy to answer. Julian, is there anything that I need to address, or is it fine? Hello.
Your explanation was just great.
What's the orange line indicate? Okay, thanks, Julian. And if you want to, do you want to add anything on top of it, or like, if I went wrong somewhere, just feel free to.
No, it was just great.
Yeah.
The decision boundary really depends on the method. So
Yeah,
I guess that is something to add.
Yeah, that's
So
totally, I agree.
In logistic regression, we have this approach of decision boundary. But if you use support vector machines or random forests or decision trees, the decision boundaries are going to be totally different.
Right.
So
right.
that is something to add in your explanation, maybe.
Yeah, I agree. Yeah, maybe you can add some more points on top of it. And I'm just addressing one of the learners' queries. So yellow line is nothing but the ideal fit. Like, if we have to compare these two things, right? So here we have drawn the decision boundary as green. However, intuitively, if we look at it, if we draw the decision boundary here, all the points which are on the left would be classified as those individuals who don't have an insurance. All the points which are on the right will be classified as those people, like, who have an insurance. Okay, that is our prediction. So it would have been ideal had our decision boundary been this yellow line instead of green. So that's what I was trying to explain here. Like, we can just simply skip this. Okay, there is it has very little relevance. That's mostly used for explaining the intuition behind the decision boundary. Okay. Yeah, Julian, it's I think, like, you can take over now.
All right.
And yeah. So we have So you want to add something on top of it? You wanted to discuss something about the decision boundary, right? Maybe you can explain that, and then I'll ask next question.
No, I guess it's pretty clear. I don't know if there are some
Yeah.
questions regarding the decision boundary instead.
No, I think like that's pretty much. So next is how to dive deeper into statistics, probability, the math behind data science and ML. Okay, this is a very generic question. I guess you can address. Yeah.
So statistics in ML approaches are really deep. So if you take, for example, linear regression and analyze the equation, that would be great. That is simple math and algebra. So you can analyze how the equation is forming that linear relationship between the features and the target variables. But if you want to address the statistics of a neural network, for example, or for a PCA or for a random forest, that is going to be quite difficult at first. So I recommend you to maybe analyze first what the distributions are, what probabilities are, what the linear equation is, how is related linear equation with the equation of sigmoid logistic regression. And then I start diving a little more instead of jumping from linear regression to neural networks and backpropagation, because that is going to be very difficult to address. So I guess here in the bootcamp, we are doing just great, going step by step, and then you'll get all the knowledge about the statistics and math behind maybe more difficult models.
Yeah. No, I second that. And we'll probably pick next question. If we want to check for null values, is that part of EDA or data pre-processing stage? If there is no null value, can we skip EDA?
Yes, it is part of an EDA. Actually, it's part of data wrangling process. Some authors split this EDA between data wrangling and real exploratory data analysis. So I'm just talking about that. We have a first step of data acquisition. I'm talking about the pipeline in data science. So we have first step data acquisition is just acquiring data. The second step should be data preparation or data wrangling, which is structuring, cleaning, and enriching your data. Trying to impute or analyze missing values is one of the steps in the cleaning process of data preparation. So this is just the second stage in this pipeline. Then we have the exploratory data analysis, which is just analyzing how the data is distributed and what we can delve from this data. So maybe you want to split these two stages into data preparation, which is structuring, identifying missing values, enriching the data set, etc., and then exploratory data analysis. So if you don't have missing values, it's just one of the stages in data cleaning, and it is just one of the stages in data wrangling. So you have to perform a data wrangling process with no missing values, and then perform an exploratory data analysis. So the steps are the same, whether there are missing values or there are not.
Yeah. And yeah, so coming to next question, I think this is troubling many people big time. Okay, actions to be taken on the observations we draw from EDA. For example, no correlation, linear relation between Y and X, what should be done? So basically, we end up doing a lot of exploratory data analysis, and we draw some conclusions, or not conclusions exactly, but we draw some inferences. So what do we exactly do with it when it comes to model building?
Okay, so it depends if your hypothesis needs to be tested. So if you want to test your hypothesis, then maybe you want to perform hypothesis testing or chi-square test or ANOVA or whatever the test is. If you don't have the clear context, so if you know how to associate this hypothesis to the context, then probably you don't need to perform a hypothesis testing, because you know that it's going to be statistically significant. But if you don't know how this hypothesis is related to the context, and you have found just a very new hypothesis that is going to change the world and change the context, then you will need to prove this hypothesis because you don't know if it is statistically significant or not. Then when you have stated your hypothesis and you know they are significant, you start building a model. So you know that this model is based on your data, on the nature of your data, and on the hypothesis that you have stated. So if you identify this is a classification problem, and you identify this is a multi-class classification problem, and that the data is coming from different sources, you know what model to be applied. So you're not going to apply logistic regression single model because this data comes from different sources, is multi-class, and you will need to select the adequate classification model. So all these hypotheses and this exploratory data analysis for analyzing your data and identify the nature and the source of your data is helping you on identifying the best model to be fixed into the data.
Right.
So this is a very empirical procedure. Always, it always depends on your data, what you have on what you don't. So you'll need to analyze and to make the exploratory data analysis and to state hypothesis before building a model.
Right, I agree. So it's more statistical and like where you want to test your hypothesis. That's when it comes handy, right?
Yep.
Yeah, great. And so far, like we haven't gone deep into it apart from what Professor Julian has taught us in his session on exploratory data analysis while using cybersecurity dataset. So that was one session where we tried to test hypothesis. That too, like we didn't go deeper there, and yeah, so that's some context to everyone. And now, like we have one question on YouTube: what percentage of missing values in a data can we ignore or drop? Also, when to go with mean and when to go with with median for numerical data.
Okay, the general answer is there is no percentage. It's just a recommendation of if you have 20% of missing values, then you can possibly drop those missing values. But it really depends on the nature of your data, as I always say. So perhaps you have 0.0005% of missing values, and you don't want to drop that rows because they are important to you. So it really depends on what the desired output is and what the important features are, if you decide to drop them or not. So this is very empirical. There are just suggestions and guides that state that 20% is the adequate percent for dropping or having the rows. But it really depends on the nature and the analysis from your data. When to use median or mean? Well, the average is just a classical calculation. Maybe the median is going to help you when you have a lot of outliers. So the median helps a lot when there are outliers because it's not sensitive to outliers. The median is sensitive to outliers. So the mean can vary a lot if you have one outlier at the top or one outlier at the bottom. So I just want to share the screen to explain me better. So if we have a distribution, I'm just gonna draw a box plot. So I guess all of you have seen a box plot, right? So you have this box plot, which is stating the distribution of your target variable. So let's say this is my feature. I'm sorry, and this is the distribution. So we have here probably is frequency. If I have an outlier above here, then the mean is gonna be altered, and the calculation of the mean is gonna be incremented. If I have a lot of outliers here and one outlier here, the mean is going to be updated and it's going to be variated according to the outliers. So the mean is very sensitive to these outliers that I am drawing at the top and at the bottom. If this happens and I have a lot of outliers, then I would probably choose the median because the median is not sensitive to outliers, and the median is going to be barely over here as I'm drawing, and it's going to change a little. So whether to use mean or median really depends on the distribution of your variable. and when to impute with median or mean, it depends on the distribution of the feature that you want to impute. It is not advisable to impute the values, however. So you have to analyze the nature of your data and identify if you really want to impute the missing values with the mean, for example, because that is going to alter your distribution, and that is going to alter a little bit the nature of your feature. So you have to analyze whether to impute the values or whether to drop the values or whether to keep that missing values. That is really the key point in here. Once you have identified that you want to impute the values, then you'll decide if you want to impute the mean because you don't have many outliers, or you want to impute using the median because you have a lot of outliers in that variable.
Yeah, thanks a lot, Julian. And next question is, so this is again a very basic question, and again, like, where people are generally getting confused. What does X train, X test, Y train, Y test contain?
All right. I'm just going to share my screen again. I'm sorry if I use Paint. I just love Paint for drawing
No
and
problem.
displaying. So imagine you have your complete data set in here. So you have a lot of observations in your data set. If you train over the complete data set, then you won't have observations for testing. So the key idea when modeling is to show the model the observations that he must learn, and then to test if he have learned right or wrong. So for doing that, you have to split this data into some observations for showing the model and some observation for testing the performance of that model. So if it is similar that if I have my model and my model is just a boy of 5 years old, I am just going to show him what is a pen and what is not a pen. How do I test if he have learned right or wrong? Showing another type of pen that he hasn't seen before. So it is just the same. I just want to show the model some portion of the data so that he can learn, and some portion of the data that he hasn't seen so that I can test whether he has learned right or not. So here it comes the training testing split. How is this addressed? Maybe I just want to split my data set in here, but this is probably going to be a bias because I choose whether to split my data into training and test with a single decision boundary like this one. It would be a bias because maybe these observations in the right, in the left, are of different nature than the observations on the right. So instead of doing this, I'm just gonna split into training and test randomly. So I know that I want to have 80% of my data to be the training and 20% of my data to be the testing. So if I have, let's say, 1,000 rows or 1,000 observations in my data, then I want to be 800 observations to be the training and 200 observations to be the testing. This split is going to be random. So I as a developer, I'm not going to choose what observations to be in training and testing. That is going to be random. So the algorithm is going to choose what observations to pick for the training and what observations to pick for the testing. So you can see here in my data set that perhaps the algorithm has chosen these observations to be training, this one that I am marked with an orange X, and perhaps these observations to be in testing. And that is going to be right, because that is just a stratified random splitting. So when you call this train test split, it's doing just this, splitting your data randomly, choosing observations for picking up to training and picking up for testing. What the names comes from. So you have pretty fancy names in here. So this is just the standard. You have X-train and you have X-test, right? So barely we have split this data into train. I'm sorry if my sliders are not so fancy. and into test. So when you split in train and test, then you'll need to identify what the features in the train are and what the target variable in the train is. So this train is then conformed by the features and the target variable. And this test set is conformed by their features and their target variables. So you have two sets, training and testing, and the training is just conformed by feature target and the test is conformed by feature target. So that four groups are stated in this function. So X train are the features of the training set. X test are the features of the testing set. Y train is the target variable of the training set, and Y test is the target variable of the testing set. So you have split this original data set into four groups, one for training, features target, and one for testing, features target. And that is why we are writing here X train, X test, Y train, Y test. Those are the four groups. And then, of course, you're going to have the observations split into features for training, target for training, features for testing, and target for testing.
Right. Yeah. Thanks a lot, Julian. I think, and also just to add to it, we also added one specific section today for this particular concept, data splitting, so that it is very clear and intuitive. I think we have put a flow chart for it, similar to what Julian has drawn just now. I think you can also go through that for further reading. And this video will also be put up on YouTube, so you can also go through that. And adding to this, so we have few more questions. What is the difference between decision tree classification, decision tree regressor, and linear regression? Their evaluation methods, but probably we can make it short or yeah.
Okay, so they're pretty different. When you talk about classification, you are approaching a classification problem. So you have decision tree classifier, you have support vector machine classifier, you have random forest classifier. So everything that approaches to a classification problem is a classifier. So those three that I have named are classifiers for classification problems. When you have a regression problem, you are going to use a regressor. So you have decision tree regressor, linear regressor, and all other models that are regressors. So classification, classifier, regression, regressor. Difference between decision tree regressor and decision tree classifier is because one is used to is used for linear regression approaches and other type of regression approaches, and decision tree classifier is used for classification approaches. So both of them are doing the same, are structuring a decision tree and some key boundaries in there, but one is used for regression, continuous variable, and the other is used for classification when you have binary or multi-class classification problem. So the name is stating right, decision tree classifier for classification, decision tree regressor for regression. And the linear regression is pretty different from a decision tree regressor, because in decision tree, you are structuring a decision tree. So it is a tree with leaves and nodes that are helping you decide what the output is going to be. And the linear regression is just an equation that relates your feature with the target variable by a linear equation. So they are pretty different between them.
Yeah, thank you. And we have one more question. Yeah, at this, I just wanted to add something to this. Yes, regression is, as Julian said, we are talking about a regression problem, and classification is a classification problem, right? Where we are classifying certain things. Whereas when it comes to logistic regression, people often get confused. Even this was asked by a bunch of people. But logistic regression, though the name says regression, it is primarily used for classification when it comes to logistic regression. So that's the only thing that you need to remember. Don't get confused with the names. Yeah. And apart from that, my question is that if the data variables is not related to each other, so what model we build?
That question is very broad.
Yeah, that is very broad. So maybe like, we can take it a little later. It's pretty, yeah, very broad. So I still have some confusion on predicting the model and evaluation of model. Any custom cheat or recommendation based? Yeah. So basically, if you can remove that confusion on like, how to predict and evaluate model, maybe if you can summarize a bit on that particular pipeline. And
All right. Prediction is just trying to identify what the target variable is going to be as the output. And evaluating is predicting and identifying what is the performance of the model. So one thing is just for predicting the variable, the target variable. So if I am predicting whether my image is going to be from a cat or from a dog, then the prediction is going to give me cat, dog. And for evaluating, then I just have to predict all the observations, whether my observations is from a cat or from a dog. And then I'll just need to evaluate that predictions against the real values so that I can evaluate the performance of the model. So one thing is just for predicting the output, and the other is for evaluating the performance of the model. And the performance can be evaluated using several metrics, such as accuracy, F1 score, sensitivity, specificity, or other metrics.
right, yeah, totally agree. And yeah, and also like, just to give you a heads up, tomorrow we have another session specifically targeting the model evaluation metrics that Professor Julian has just mentioned. So we'll delve deeper into it. And as he mentioned, like, technically, like, we have built a model and now we'll have to evaluate and test its performance, right? How it is performing on an unseen data. So that's what we're going to learn. And apart from this, and also one more question that we have. So can you suggest from where can I get the data sets similar to which you explored in your cybersecurity session?
Okay. The dataset from my session is a real dataset from a company from the United States. I have cleaned some variables so that I'm just stating public data, not private and sensible data. So of course you're not going to find this data set publicly available because it's a company's data set. But how can you construct or structure a similar data set? It depends on your question. So as I always say, it is not about data science procedures. It is first about the context. So you have to state a question and you have to state a problem, a business problem, so that you know what the horizon is and what you want to solve. Once you have this problem statement and the question, then you start acquiring your data. So you know what the data is going to be, you know what the data is needed, then you start acquiring your data. So this data was very difficult to be acquired because there are plenty of cybersecurity attacks going on in a company, and this is a sort of sensible information in here. But we did some operating system procedures to acquire this data, visualizing the logs and the, I don't know how to state it this simple, analyzing the data that the operating system is generating in order to conform this data set. And then we classified those attacks into exploits, denial of services, or whatever the subcategory of cybersecurity attack is. So it is a pretty difficult process of acquiring your data, depending on what the question is. If my question is just, have I been attacked or not? Then the data is not so difficult to be acquired because I just need some data that states whether I have been attacked or not. But if my question is how to detect patterns in cybersecurity attacks, then the data is going to be very difficult to be acquired because I will need a lot of properties and attributes in this data. So it really depends on the business problem and the questions data.
Right, right. Totally agree. And also maybe like, people as someone has mentioned, people can also use Kaggle and different other websites to find, obviously they can't get the real data, but they can probably get some data to play around. Right. And one more out of box question. How hard will it be for a 14-year-old to achieve their data science dream?
All right. It's a very interesting question. Well, I don't know what your data science dream is, but if you're talking about applying data science to certain context, it's not going to be difficult. You first need to know about the context. This is always the key aspect. It is not about data science, really. I mean, data science is just joining mathematics, statistics, computer science, maybe software engineering, and a bunch of sciences in here. But if you don't know about the context, then data science is just innocuous. So the very interesting here aspect in here is learning about the context. So if you're interested about astrophysics or soccer or cybersecurity or whatever the context is, I really recommend you to analyze, interpret, discuss, and learn more about the context so that you are able to perform data science techniques into this context. So it is just applying mathematics, statistics, software engineering, and a bunch of other sciences to the context. And it's really important for you to know first the context and then apply certain data science techniques.
Right, I totally agree. Again, like, that's very insightful, I guess. And it also depends. It's very subjective, as in, like, what the dream exactly is.
Yeah, yeah.
And yeah, I totally agree. And probably, like, I'll try and add some context to it based on my experience in managing communities and working with communities at CodeChef. So basically, I met this particular person. I mean, like, I got to know about this particular person called as Malvika Raj Joshi, who is a homeschooled girl, and she went on to compete at IOI World Finals. You know IOI, right? International Olympiad in Informatics. So she has basically, like, participated in that, and I think Professor Julian will be knowing more about it because he comes from a competitive programming background. Like, there is international Olympiad in physics or mathematics, and there are a bunch of Olympiads, right? Similarly, there is something called as international Olympiad in informatics. So she fared very well there, and then she went on to do her bachelor's in MIT, and she got an admit there by the virtue of she competing at this prestigious competition, and, like, because of her profile and bunch of other things. Whereas yeah, so that's some context about her. Similarly, like, we have, coming to data science, I think we have a similar competition websites like Kaggle. Okay, what we can do is potentially we can be active in communities where there are plenty of data science challenges that are happening, and try to contribute to the community at the same time, try and participate in the challenges and showcase our skills there. And I'm sure, like, there will be plenty that we can do on that front. And also at the same time, we can pick some personal projects or whatever it is to fare well in that particular domain. So that's some general advice. And also, someone is asking about okay, how to please explain pairwise deletion.
All right. Pairwise deletion is pretty advanced sometimes. You have pairwise deletion or lightwise deletion. It depends really on the nature of your data again. So the pairwise deletion is just considering all other variables and features. It is one of many types of deletion when you are treating missing data. So I I don't I don't want to explain deeply what pairwise deletion. I'm just gonna state again that it really depends on the nature of your data. So when to apply certain methods, it really depends on the desired variables, on the impact of deleting the rows, on dropping the rows, imputing the rows pairwise, considering other features. And it really doesn't depend on what the nature of the method is, but what the nature of your data is. So that would be my first answer to the question. Then maybe in the bootcamp, we would like to go deeper in what the deletion method is, but it really depends on the nature of your data. So don't get overwhelmed on how the method works, but on how your data is arranged and when to apply one method or the other. That would be more important.
Right, agreed. And okay, again, like, we are getting into the statistic part of it.
Yeah.
Someone is asking, what is covariance?
All right. Covariance is just a measure on how one variable is varying with another. It is similar to the variance, but is stating the relationship between the how one variable is changing within the other. So how this relation is working. That is the covariance.
Right, got it. And so someone is asking, could I use the data set that you used for cybersecurity analysis for their own research purpose, or will it be any violation of data or community rules? So this might be a tricky question for you, but yeah.
Yeah, it is pretty tricky. Well, that although that data set is public to you, I would suggest perhaps that you dive a little more on what the goal is, what the analysis is to be performed over this data, so that I know what you are going to public or what you are going to research on. That would be my advice, since this data set is property from the Pontifical Bolivarian University. So in order to be safe in the rights and the intellectual property, I would suggest you to tell me what the research is going to be, and perhaps I can guide you on how to perform this research so that no intellectual problems and issues are arised.
Yeah, thanks about that. And how to work with one hot encoding imbalance dataset, and better insight on how to know which variables to omit or not. Okay, it's again a pretty broad question where we are talking about one hot encoding imbalance dataset, and variables to omit or not, which has got to do with feature selection. But I'll leave it to you to address.
Well, the very broad answer to that broad question, it should be, first, you'll need to know when to apply what encoding method. So you have generally label encoder or one hot encoder. So if your variables are ordinal, it means that they have an order, then you'll need to apply label encoding. If your variables are, if your variables are ordinal, then one hot encoding, and if the variables are nominal, I mean, there are no orders that you can visualize, then you can apply the label encoder. So when to impute values and how the imbalance of these classes are related with this encoding is a very broad question. They are related somehow, but one thing is performing what hot encoding in certain classes and categorical variables, and the other thing is how to handle imbalanced data sets. So there are other bunch of techniques apart from these encoding techniques to handle these imbalanced data sets, and maybe you can apply them without a relationship.
Great, thanks. And okay, this is again a very trivial question, I guess. Do we need to understand every step from cleaning the data up to building the model? I can probably address this directly. So yes, I mean, like, we need to understand what's going on, but Julian, maybe, like, if you want to address something on why it is important, or what is the prominence of understanding each and every step.
Yeah, because the last step is modeling. I mean, if you look the pipeline or you look, for example, the CRISP methodology for data science, one of the last steps is modeling. So you have a bunch of previous steps, which are data acquisition, data preprocessing and wrangling, exploratory data analysis, and then you have this modeling stage. So it means that it is pretty important to understand what the nature of data is, as I always state. How structured is your data? What are the missing values? How is the impact of your missing values in your data? How to impute these missing values or to drop them or to not to do anything? How to analyze this data? How to identify patterns? How to test hypotheses if you have certain hypotheses? And then doing all these steps, you can start modeling. So data science is not modeling. Data science is not random forest. Data science is not convolutional neural networks. It's not about complex modeling. Neither is about modeling. Data science is about understanding the context and knowing when to apply what techniques. If those techniques are regarding modeling, good. If those techniques are regarding just exploratory data analysis, good. As you have seen in my session for cybersecurity analysis, I didn't model anything. So it means that it is not demanding to model or to make modeling, machine learning, deep learning. It is not demanding. So you are able to answer the questions just making an exploratory data analysis, stating hypotheses and testing them. So I would answer it like this. You don't need to model all the time. You just need to model when you want to predict some class. If you want to analyze your data, then do exploratory data analysis and skip this modeling stage, because data science is not about modeling. That is just machine learning engineering. Data science is about understanding the context and understanding when to apply certain techniques.
Yeah, got it. Yeah, I think that's brilliantly put. I totally agree on that. So before we wind up, like, I'll just pick one last question, though we have plenty other questions. So would like to know more about underfitting and overfitting. I think yeah, we already discussed about it at the right at the beginning, but probably, like, if you can explain in a few
All right.
sentences. Yeah.
Yeah. So underfitting is just when your model is not able to detect any of the classes or to make an accurate prediction from your target variable. That would be underfitting in short words. And overfitting is when your model is detecting even noise from your data, and it is arranged so that almost every point from your feature are connected. So it is just very specific to your data, and it is not generalizable for other types of data. So one thing is not detecting anything, and the other thing is just detecting everything. Both sides are dangerous. So you don't want to detect anything, but you don't want to detect everything. Both sides are very dangerous. So you want to be in the middle, detecting something, but not detecting everything, because detecting everything is also dangerous as detecting nothing.
Yeah, exactly. So basically detecting everything is like when you expose it to unseen data in future, I mean, it might perform well with your existing data, but when it is exposed to new data, it may go for a toss, right? It may not perform well.
Yep.
Yeah, great. And one last question before we wind up. If two independent features have correlation equal to 1, then is it okay to drop one of the feature? This is again, like,
Right.
yeah, go ahead. Yeah.
Yeah. Well, it is going to be pretty difficult to have a correlation of one. It is as difficult as have an accuracy of one. But if your correlation is high, I mean high of above 0.8, then you have two options. Keep both variables and maybe merging together using different types of merging and relationships, or deleting one of those two variables. Both of the approaches need to be tested in order to identify whether to drop this variable or whether to make an interaction between both variables and conform one. These two options are performed where the correlation between the variables is high, and high is above 0.8 or below minus 0.8. This is going to be high for us, the absolute value above 0.8. If you have a correlation of maybe between 0.5 and 0.7, that is not going to be pretty high. That is just going to be a correlation between 0.5 and 0.8. So what to do in this case, just keep the variables and try to test with those variables and without one of the variables so that you can prove your hypothesis and you can see what the accuracy is between those two approaches.
Yeah, got it. Yeah, thanks a lot, Professor Julian, and thanks for your time. I think even on YouTube, thanks a lot for all the audience out there. And thanks to everyone who have come on Zoom. Naresh, we will address your questions independently. We have seen your message. Okay, thanks. Thank you. And have a great evening or good morning to Professor Julian. He just, I mean, it's too early in the morning out there. Thanks a lot for readily agreeing to do this. Thanks a ton. And take care. Bye.
Bye.